Hmm.
Hello ma'am, I'm Vishnu.
Hi ma'am, good morning. I am Pratham Mishra.
So our project is regarding design analysis of second order and third order bandpass filters. Our aim was to design a bandpass filter of order second order, third order, which is useful for better filtering of some biomedical signals.
And yes, we have came up with different types of band pass filters. So our main agenda was to compare second order and third order band pass filters for biomedical purposes. So we had to actually check how the band pass filters work and what criteria do we have to fulfill for our band pass filters. So firstly we can see that what is a band pass filter. So band pass filter basically is a filter which allows a particular range of frequencies of a low range and a high range to pass through it, and other frequencies are usually diminished or cancelled out. So for our project we had to design a band pass filter which had a lower limit of 0.5 Hz and a upper limit of 100 Hz. This limit was decided considering the limits of the ECG signal, which again was for the fact that our project was given to be made for biomedical signals. And now we can see that the order of the filter actually determines the slope, and we can actually see that as the order increases the graph gets getting steeper and steeper. So we would have a better fall if the order gets on increasing.
For first order, we would have a roll off of minus 20 dB per decade. As the order increases, the roll off increases as in the order of minus 20 dB. Like for example, for the order of first order, the roll off is minus 20 dB per decade. For the second order, the roll off is minus 40 dB per decade. So as the slope is getting decreased, we would be the amplitude values at that point would be attenuated faster.
And so this is our design approach. We have for second order band pass filters, we can combine a second order low pass and a second order third pass, and we can combine it through a buffer, and similar things can be done for the third order band pass filter. And here we can see our design approach, like how we came to our design. Basically it was very confusing for us to choose one out of Butterworth and bezel filter, because as we can see that Butterworth was offering us a better roll off, so the frequency values would attenuate more sharply. On the other hand, bezel was also good, but Butterworth was more better, giving better roll off than bezel. And the other Chebyshev and elliptical had ripples, so we did not consider it because we have to be precise about our values and we would like to have zero errors. So due to the fact of considering errors, we had chosen bezel because it gave us linear phase, unlike the phase in the Butterworth, which was not linear. So here is the diagram of circuit diagram of Butterworth band pass filter. We can see a second order band pass filter which was combined, with a second order low pass and second order high pass. And we can also see a third order band pass which was again combined with a third order low pass and third order high pass filter. In this circuit diagram, it was working fine in the simulation, so we didn't need buffer. But when we actually implemented in on hardware, which was our bezel filter,
We used a buffer in between the low pass and the high pass.
this is a circuit diagram of Butterworth and the calculations for Butterworth.
The calculations are taken from the 14th chapter of the Texas Instruments book, which was referred. The book will be attached in the report itself, and based on the calculations there would be some fixed coefficients for each of the filter. So as we see, the calculations are based on the second order low pass filter. For every filter there would be a coefficient, so we chose the Butterworth coefficients of the second order low pass filter. Then we have use it in the calculations. Like as you see in the A1 and B1 are the coefficients here, which are standardized. So directly we can't change any resistance values manually because that would affect the circuit and the coefficients. And for every circuit we made same calculations. As you see, we have attached calculations for all the filters which we used, like for the low pass and for the high pass individually. So as we see, this is the Butterworth bandpass filter. It requires whatever third order, it requires 4 op amps, which consists of two. As we are using a third order, we need to cascade a first order and a second order filter for the low pass. And coming to the individual calculations, those are attached already, as you see in the slides. This is the individual calculation for first order and second order, which belongs to a third order bandpass filter.
We can see the calculations. We would not like to explain them in the video itself because it would be attached in the report as well. So similarly we can see bezel. Actually this diagram actually differs from our hardware implementation. In hardware we have used a buffer because our circuit wasn't responding, I mean it wasn't giving us the value we needed. So we actually took help of our assigned TA Vamshidhar sir. He told us it would be great if we could attach a buffer in between the low pass and the high pass, and it actually worked pretty well. So here are the calculations for bezel. Again it is referred from the same textbooks. We can have coefficients of the coefficients we used in these calculations are actually mentioned pretty well in the textbook. Like for the second order we have A1 and B1, and when we come to third order we get A1 A2, and similarly we can get coefficients for higher order as well.
So these are the plots for the different bandpass filters, and as we know that we made two filters in the simulation, namely Butterworth and bezel. We need to compare them. So these are for the comparison. As we see here, the red line indicates the second order and the green line indicates the third order. Based on the order, the steepness is decreasing. So if we take some amplitude, if it's some frequency, the amplitude will be attenuated. Like if the frequency is around 150 hertz, the attenuation here would be more because the unity gain is decreased here. Same with the bezel filter. And coming to the phase, the linear phase is more in the bezel bandpass. So we chose to use bezel bandpass
filter
because that would help us in less distortion when we transmit in the channel. And coming to the simulation, we also calculated the distortion analysis, which shows us how much our signal is distorted after the transmission. So for the second order bezel we got around 1.08, and for the third order bezel we got around 1.57% in the distortion, and the distortion curve is attached at the right side of the image. And next we need to find the distortion in hardware itself. So we took the FFT plot in the DSO and changed the the Y scale to the RMS voltage scale, and we noted the RMS voltage at different fundamental frequencies. So here the fundamental frequency we chose is 10 Hz. So at 10 Hz we chose the signal, and we got around 1.7% of the 1.7% distortion.
Now moving on to our hardware implementation, we implemented our circuit in two ways, the breadboard and the PCB as well. So we need to choose a range of 0.5 to 100 Hz, and we used a US741 op amp for our hardware implementation. Then we implemented the same circuit as the simulation of the bezel bandpass filter on our breadboard firstly. So when we implemented our hardware, we can see that we got it around, like on -3 dB we got 97.3 Hz, which was actually not 100 Hz, but it was pretty close to it.
Since our hardware is not that accurate, like resistors and every other things has their own non-linearities, and based on those non-linearities we can't expect a minus 3 dB at 100 hertz, and there would be some changes. Like as we cascade the stages, the error would be increased, and for single in the second order band pass, we use the single low pass and single high pass, so the error would be very less compared to the third order. So as we move on to the next, in the plots, we can see in the DSO plots the level of we have a constraint of the DSO here. The DSO was unable to show the frequency Bode plot at less than 10 hertz.
So we could not get a complete Bode plot.
To ensure that we show that the high pass is working, we attach the plots here. Like as you see at 600 millihertz, the output was around 840 millivolt, and as we increase the frequency at 500 millihertz, it was around 760 millivolts, and at
200 millihertz it went
it
down
was
to
like
300
millivolts.
So as you can see, when we go below 0.5 hertz, our signal starts to attenuate.
The same thing with the minus 3 dB of the high pass. Like we got around at 100 hertz, we got like minus 3.73 dB. So and the images at the DSO shows us how the attenuation is there in the 900 millivolt and 1 volt. Like as you see, there is a attenuation of at 80 hertz we have 900 millivolt, and at 50 hertz we have 1 volt, like which is the same signal. So as we move on to the 100 hertz, the signal gets attenuated, the unity gain decreases, because there would be the signal would be passed in between both the frequencies, and as we reach the 3 dB it gets decreased. And coming to the disruptions caused in the hardware and simulation, we tried to use some different analysis to reduce the things. So as we see, first of all we thought about temperature analysis. So how does temperature affect in the circuit? So to ensure that temperature is affecting or not affecting our signal, we tried to simulate the things using the microcap software. In the microcap software, we use the capacitance coefficients of the temperature. Like there would be two temperature coefficients, namely the linear coefficient and non-linear temperature coefficient. So based on that calculations, as we see, there is a different range of values here. As the temperature increase, there is a spectrum formed. So at 27 degrees Celsius, our temperature was around minus 3.10 dB in simulation. At 50 degrees Celsius,
it went down to minus 5.86 dB. So as we can see, temperature played a major role in deciding the simulation. So we thought that this might be one of the reasons why our hardware implementations are getting a slightly inaccurate output, and it actually was. So we came down and we discussed with ma'am and our TA. So he told ki temperature might be a factor in our inaccuracy, and the other factor might be the resistance and capacitance which breadboard offers.
a parasitic capacitance.
Yes. So to reduce that, it would be better that if we implement our circuit on the PCB. So we actually came down to the PCB circuit. So as we can see, we use soldering lead to connect the wires, which actually has more conductance than normal wires. So it might reduce any of the resistance which was offered due to the breadboard, and we hope that we would get a better output, and it actually was slightly better than what was in the breadboard.
We haven't seen any major changes, but coming to the hardware and the breadboard, the outputs were almost same, and they were better compared to the breadboard ones. And coming to the input and output impedance, we have used the software LT Spice, where we have given a test source for the input, and we have taken the as we know, the input impedance is calculated by giving a test source and finding the resistance at the input. Like we given a test source of 1 volt, then we divided for finding the resistance, we calculate the ratio of voltage and current, so that we would be having a input impedance and the output impedance can be calculated easily using this procedure. And our main challenges was temperature and resistance with an inaccurate resistance, because every resistor has its own tolerance level and every multimeter also has its own tolerance level. So proposed improvements and concerns, we can use as an improvement, we made the circuit in the soldering by using soldering and breadboard. We compared both of the results, we compared the second order and third order results, and our cutoffs were almost good enough, like around 5 to 6 hertz difference. We are getting a 3 dB point. And as you see, we have done many analysis. We learned about most of the things in the project. This project helped us in understanding how it is hard it is implement a small circuit or a large circuit in different scales of the hardware.
And also the project helped us to discover the various types of filters, namely Bezel and Butterworth. So we got to know about the different coefficients. Actually, before doing this project, I didn't know much about the coefficients, and also we used to calculate, the frequencies directly based on the formula of 1 by 2 pi fc or something. So when we got to know that different filters and different orders in specific have different coefficients for calculations of the RC values, which actually gave us more accurate filters than we designed before.
Thank you.
So we would like to thank Anshu ma'am and our assigned TA Vamshidhar sir, who helped us throughout the project and uh, helped us in learning various things about filters. Thank you so much.
Thank you.